Hello. Hello, ma'am. Yes, ma'am. We are hearing you. No problem. உங்க பேசுறது கேக்குது, ma'am. Okay, sure. Sure, ma'am. So good morning, all.
Good morning, ma'am.
Good morning. Um, dear participants, today we are going to start our two-day international conference on novel nanomaterials for innovative research. And the day starts with a prayer song. So, now I'd like to call upon Dr. B. Prakash to deliver the welcome address.
Thank you.
Thank you, sir. So, thank you for your valuable welcome address. Now, I'd like to welcome our Dean, School of Science, Suresh sir, to present his present inaugural address.
Am I audible?
Yes, sir.
A pleasant good morning to all. Respected Dean Research and Development, my colleague, Dr. KPV Sabaresh, the resource persons, Dr. NB Reddy, Inspector of Research Hydropaper, Center of Excellence in Transportation, Electrification and Energy Storage, Canada, Dr. Rajesh Kumar Modi, Research Scientist, Micro and Nanotechnology Center, Tokai University, Japan. Beloved head of the department, Suma Maheshwari, the faculty members, students, and participants. A warm good morning to all. It is an honor and privilege to be part of this international virtual conference on novel nanomaterials for innovative research and then to delivering this inaugural address. The true sign of intelligence is not knowledge but imagination. Imaginations led to the discoveries, great discoveries, and base for the inventions. First, let me congratulate the department for the theme of the conference. Coming to the nanoparticles research, nanoparticles research is a fascinating branch of science. The strongly size-related properties of nanoparticles offer uncountable opportunities for surprising discoveries. The often unexpected and unprecedented behavior of nanoparticles bears a great potential for innovative technological applications, but also poses great challenges to scientists. They have to develop a highly controllable synthesis approaches, more sensitive characterization tools, and finally, new models and theories explained in experimental observations. The theme of the conference is apt, and I hope this conference will serve as a platform for sharing the knowledge, understanding the developments in the area of nanoscience and innovations in research. I congratulate the head of the department and their faculty members for organizing this international conference, and I wish the conference will be a huge success and to be conducted every year. With this small words, I conclude my speech. Thank you all.
Thank you so much, sir. So, thank you for your wish and valuable suggestions that you have given us in throughout this journey of starting from end. Thank you, sir. So now I would like to welcome our Dean R&D to give away the presidential address. Sir.
Yes, ma'am. Thank you, ma'am. Thank you, ma'am, for this opportunity. First of all, my special thanks to esteemed chief partners and also partners for granting support for organizing these conferences. And it is my privilege to be part of this conference, and I welcome you all to the International Virtual Conference on Novel Nanomaterials for Innovative Research, Icnnir 2021. This is our first virtual conference organized by Department of Physics. Thanks for this COVID-19 pandemic made us an alternative and more effective, and we can say as an innovative way to conduct this conference in more cost effectively. Importantly, thank you to the invited speakers, Dr. Ganesh Kumar Mani from Kyoto University, Japan, Dr. M.D. Reddy, Center of Excellence in Transportation, Electrification and Energy Storage, Canada, and Dr. Jagadish Kopalas, S7 from University of Hamburg, Germany, and all the participants from various institutes and universities for your wonderful support to make this conference happen. The conference will focus on innovative research happening on novel materials. And here, the thrust areas include nanotechnology, nanoscience, material science, bioscience, biomaterials, engineering science, and also we are also interested to know about theoretical and computational physics related to nanomaterials and all other thrust areas in common science. So far, we have received 100 plus interesting abstracts, oral presentation, poster presentation covering all these research areas. Both speaking will give us an overall concepts and innovations happening in nanomaterials and their potential applications. And this will guide us to move further to the goals for the betterment of society and for it. I would like to thank the conference convener, Ms. D, for taking all this effort, and special thanks to organizing secretaries and also invited speakers and participating faculties, research scholars, and students for your kind support and make this conference successful. Thank you so much and stay safe.
Thank you, Sabri sir, for your valuable speech and valuable suggestion. Now I would like to call upon Uma Maheshwari ma'am to give away the dynamics of speakers. So good morning everyone and a warm welcome to you all, and hope you all safe in your home, since because of this COVID situation everywhere the research spreading is over. So be safe and be healthy. So from our Department of Physics, Ratnam College of Arts and Science, so we are organizing a international virtual conference on novel nanomaterials for innovative research 2021. In this special occasion, I feel extremely honored to introduce the chief guest in this virtual conference, Dr. Ganesh Kumar Mani, postdoctoral researcher, Micro and Nanotechnology Center, Tokyo University, Japan. It is a great privilege to have him in this special occasion. Dr. MGK, he's completed his post-graduation in nanoscience and technology from Bardar University, Coimbatore, and he did his PhD in Sastra University, Tanjavur. Then he is working as a postdoctorate researcher for the past 7 years in Tokyo University in Japan. He has a research experience in various streams such as microneedle sensors, microfluidic sensors, gas chemical sensors, electrochemical biosensors, MEMS, fabrication, thin film electronic noses, and biomedical sensors, etc. His research interests are microneedle based sensors for single cell metabolite in microenvironments, biomedical sensors for circulating tumor cells detection, metal oxide based gas chemical sensors for food quality and healthcare, electronic skin based sensors for non-invasive disease diagnosis. The main highlights of his research contribution are: he has 60 plus peer-reviewed journal publication and overall impact factor of 230. He is act as the editorial board member for journal Censor MDPI. He written 2 invited book chapters, and 2 review articles. He has 45 plus proceeding articles in JSPE, JSME, MHS, etc. His H index 21 and has 2077 citations. He filed 2 Indian patents and 1 US patents. He is serving as a reviewer for several internationally recognized journals: ACS, Applied Materials and Interfaces, IEEE Sensors, Journal of Alloys and Compounds, Biosensors, Journal of American Ceramics Society. He is an ACT peer reviewer for elsewhere for book proposals on micro and nanotechnology. He has various industrial collaborations and awarded greater than for 45,000 US dollars so far. He won various awards such as Young Researcher Poster Award, Young Scientist Award, Best PhD Dissertation Award 2015 from various conferences and symposiums. We are very grateful to Dr. Ganesh Kumar Mani for accepting our invitation and marking his presence in this conference. Now I am inviting our resource person. I'm sorry, 1 minute. And one more resource person, Dr. M.V. Reddy. He is also one of the resource person for today's speak, and he is from Science and Engineering from University of Bordeaux, France. Sorry, he has been graduated or PhD from University of Bordeaux, France, and he is currently working as a senior research in Hydrocubic Center for Excellence in Transportation, Electrification and Energy Storage, Canada. So for today's speaker, we are having 2 speakers, Ganesh Kumar Mani and Dr. M.V. Reddy. So the participants are requested to have this resource person, and you can ask your doubts about their topic, as well as whatever things you want to ask in your research. Thank you for the opportunity. So now I'd like to call upon Dr. Ganesh Kumar Mani to give away the keynote speak for this session. Sir, welcome you, sir.
Thank you, ma'am. Thank you for your wonderful introduction. Good morning, one and all. Let me start my. Is my screen visible, ma'am?
Sir,
Yes, sir.
yes.
Am I audible? Clearly?
Yes, sir, you're audible.
Okay. Good morning, one and all. This is Ganesh Kumar Mani. I'm from Micro Nanotechnology Center, Tokai University, Japan. So today I'm going to speak about novel biomedical sensors for healthcare. So before going to the core topic, let me introduce my university first. So it's Tokai University. It was established in 1942, and we have total number of students of 30,000, and we have 7 campuses throughout Japan. And the employment rate of our university students is 98%, and the student faculty ratio is 18:1. And our university is mainly famous for 2 things. One is for the solar car, and another one is the Olympic medals. So our team Tokai has won many world titles in the Solar College Challenge, especially World Solar Challenge in Australia and Sasol Solar Challenge in South Africa. And one more thing, one important thing is we have so many athletes in our university. So till today we have our university alone won 37 Olympic medals. And Dr. Shigeshi Matsumi is the founder of our university. And we have some several research centers in the university, like Institute for Civilization Research and Institute for Medical Sciences, Micro Nanotechnology Center, and something for the marine research also. So I'm working in the Micro Nanotechnology Center. So this is the environment of the Micro Nanotechnology Center. So this is our working environment and working space. And he is a Professor Okamura. He is one of the inventor of the polymer nano sheets, which is having less than 10 nanometer to 200 nanometer thickness. This is our core research of our Micro Nanotechnology Center. So we are all the faculty and postdocs are utilizing this kind of nano sheets and using for multiple applications. So not only this Micro Technology Center, so the Technology Center is along with working with Nikon. I know many people, almost everyone know about Nikon Center, and we jointly collaboration with Nikon, and we started a new research center like a Tokai University Imaging Center for Advanced Research. So what we do here is the Nikon supplies all kind of microscope to our laboratory, and what we do is we are trying to improve the quality and the sensitivity and the image quality of that particular microscope, and then we give back to them, and they are supplying and selling to some other research institute. So actually we are developing some other tools also for imaging and for getting clear image and as soon as possible. So that's why we collaborated with Nikon and we started this center 2 years ago. And this is one of the center in the world, maybe less than 10 centers are there supplied by the Nikon, and we are one of in Japan. So going to the core topic. So today these are the topics I'm going to speak with you on basics about the nanotechnology a little bit, on point of care devices, biomimicking, microneedles and sensors, microneedle sensor, microfluidic sensor, mouthpiece and electronic skin, and what about its future. So first going, because I know many people are the doctorate and postgraduate students are there, and still some bachelor students also there. So it's my duty to give a little more introduction about the nanotechnology in 2 or 3 slides. So almost everyone know the nanomaterials, the importance of the nanomaterials, why they are using. So let me give you a brief introduction. The nanomaterials, the material properties change. The only thing, the material properties change as the size varies. So like a melting point, fluorescence, electric conductivity and chemical reactivity. And the surface size is the most important thing in the nanomaterials. So as the size is reduced, it has the more active surface, and then the reactivity of the material will change, so that all the property is changing. So you can see in this image, this is the same nanoparticle and having different size, and it is giving different colors of fluorescence at each different sizes. So that's why nanomaterials are very important based on size. So tuning the size of the nanomaterial is very, very important, so that you can get your desired property. So what is the how the nanomaterials are synthesized? Only by 2 methods. One is the top-down approach and the bottom-up approach. The top-down is like a kind of etching. So we have a big block, and then you need some desired structure, a kind of lithography. You can etch out all the part, and you can get the desired structure. And in the bottom up, you are starting from the some small particles, small say for small atoms, small particle, and small crystallites. So that is the bottom up technology. Only these 2 technologies can be used for creating some nanomaterials. Even some other new technologies also came, and let me speak about that one later. So what are the applications of nanotechnology? So almost in each and every field, we are using nanotechnology, like information, advanced material textures, energy, aerospace, healthcare, transportation, biotechnology. So today I'm going to speak about the applications of this nanotechnology in the medicine and health. So, as I said in my topic, I'm going to speak out some biomedical sensor. Sensor means to sense something. So these are the thing we artificially, because our human, we know we have 5 senses, and these are the artificially made 5 senses. Instead of our eye, we use the camera, which is having both are doing the same function, and the same as the mic and headphones, and as well as the tongue, the sweat. So this is the main topic I'm going to speak about. It's electronic tongue or electronic nose. So which is having mimicking our body senses. So what about our healthcare system? So our healthcare system, maybe now in this pandemic, you can see the many people have to work coordinated, like an ambulance driver and the hospital, as well as the patient, everything should be coordinated. That's why healthcare system is a bit more complicated system, because the specialist, primary care, laboratory, hospital, pharmacy, all should be coordinated very well to take care of the patient. That's why the more complexity came, and most of the cost of the healthcare system is becoming very high. That's why, as an alternative, the point of care devices came. So, what is meant by point of care devices? In earlier days, if the person having some heart attack or some other fell down suddenly or stroke or something, what they will do? They call the ambulance and carry them and collect sample, and they process the sample and perform test, and then result, and then finally analyze the result. Then with consultation with the doctor suggests the patient can be admitted in the hospital or go back to home. So for any kind of testing, it needs a bit more, a lot of time it is taking. That's why the point of care devices. So previously, if a person having diabetes, what he will do? He will go to some healthcare center and he can measure its diabetic level. So now, what the people do? Many diabetic people have purchased the glucometer, and they do it in the home itself. So they can do and they know the result, and then they can record it. It's one of the point of care devices. And even the smartwatches now, it can measure the heart rate and SpO2 level and as well as ECG. So previously they have to go to the healthcare center. It takes a long time. So now each and every day, whatever may the time, maybe 5 times, 10 times, you can measure and you can take care of your health very well. Those devices are called point of care devices. The main thing is time can be saved by point of care devices, and easily you can get a clear idea about your health. So you can see here, so this is the last 200 years, how the medical equipments have evolved. You can see here for the heart rate measurement as well as the ECG as well as pressure. So you can use this kind of device in the early days. But now it is very compact and very small and low cost also. So people can buy and they can measure from the home itself. And here you can see these are the other devices. Even the watch itself now it can measure ECG. So these are the devices are called as point of care devices. And what we are doing is we are trying to improve the quality of that one, and we are making it more comfortable. So how India can be benefited this kind of point of care devices? So India ranked #2 in medical tourism, and India's health capital is Chennai. Minimum 150 patients are coming from abroad every day. Why? Because the cost, some treatments may not legal in their own country, and high cost and long waiting time. But in India, we have access to latest technology, best surgeons, and low cost and less waiting time. For example, you can see here cost comparison of selected surgeries, especially for the heart bypass. You can see if you want to do the heart bypass in the US, it needs $130,000 for a single heart bypass surgery. But in India, we can do in less than $10,000. That's why many people are coming to India to take the treatment here. So for developing the point of care devices, what are the initial things we have to do? The first thing is we have to identify the biomarkers. The biomarker is the kind of a target analytes. So it has some different types. Say for example, for the glucose, say for the diabetic patient, the biomarker is a glucose. For some heart attack or some stroke, the fat level is the biomarker. So such kind, we have to find out the disease, and for that particular disease, we have to find which is the biomarker which can directly tell about particular disease. So that's why even for a single cell, if you take a single cell, it has some small molecules and proteins and fluids. So using these small molecule proteins and fluids also, you can measure and identify particular diseases. So the next step of developing the point of care devices is we have to find out the right materials. So for usually in the point of care devices, 3 kinds of materials are used. One is a silicon and its derivatives because it has a high mechanical reliability, performance, and IC compatibility. And another one is the metal and metal oxides. Usually metal and metal oxides can be used for developing sensors and actuators. So like AU, platinum, antimony, Ag, zinc oxide, like that. And polymers like polydimethyl methylsiloxane and polymethyl methyl acrylate and polylactic acid. These are the kind of polymers are commonly used in developing point of care devices because of its high biocompatibility and low cost and single use devices and the surface modification. So these 2 things are main thing before considering to develop point of care devices. So in our research, what we do is we biomimic because we take the idea from the nature and then we biomimic. For example, many people know about the lotus leaf effect. The lotus leaf has the hydrophobic surface. So the researchers started inventing using the same technology. They identified anti-wetting t-shirt and anti-wetting mobile phone screen and anti-wet shoe spray and the windshield also. not only the lotus leaf effect, people are inspired from many ideas from the nature, like kingfisher bat. So which is inspired, the Japanese bullet train was inspired by the kingfisher bat, and even the eagle's feather. It was, and then shark skin, and even the box fish also. So even the shark skin, the people have started noticing the shark can go very fast in the water, and then they started studying the skin structure, and then artificially created the cap. The same structure was created in the cap. The swimmers can use the cap, and they also can move faster, which in because the structure has the less drag force, so that the people can move very faster, and then they can win the competition. Now they are started using the shark skin caps now. Shark skin caps is not a real shark skin. They just take the structure of the shark skin and artificially created and keep it on the surface of the cap. So going to the first topic, painless microneedle. I know many people are afraid of the needle. Nearly 20% of the global population have the needle phobia because they don't want to take any injection, or they don't want to get any drugs or something because of the needle phobia. So nearly 1.3 million deaths are occurred due to this needle phobia. So that's why people are trying to invent some new method to deliver drugs to your body in a very painless way. Then only we found this one, the mosquito. Because when the mosquito bite and suck the blood, so it is less pain compared to the normal needle. That's what, if you want to sense detecting, or you want to take some fluid from your body, you can use this kind of mosquito's labium. So the mosquito's labium only can suck blood from your body. So we started analyzing it closely. You can see here, only the female mosquito extract blood at the amount of 1.9 microliter for 2 minutes. So it is taking a very little amount from your body, even though in a very less pain. You can see here the mosquito's labium is going inside your skin, and these are the blood vessel, and then it can find the blood vessel and suck the blood. So in this way, we wanted to create the same structure artificially for detection. So here you can see the mosquito cannot puncture your skin directly. It needs some vibration because your skin is very soft. So the mosquito's labium is very soft. So it cannot puncture, because if it tries to puncture, it will bend. That's why it is giving some vibration to your skin. Maybe you cannot notice it by our naked eye. So in the microscope, we have seen this. It is giving some vibration and then started puncturing, and then it can take the blood. So we want to create the same system artificially. That's what we created the system. You can see here, before that, you can see here, this is the scanning electron microscopic image of the mosquito's labium, and this is the mosquito's head, and this is the mosquito's labium. So our idea is, we want to artificially create only this mosquito's labium in the hollow manner, so that you can extract some blood or something from your body in a painless way. So we identified the size. It is 30 micrometer. So if you want to measure, if you want to create the same size, you have to use some deposition method, like a thin film deposition method. And you can see, this is the commercial needle which we are using commercially in our hospitals now. The size is 900 micrometer, but the mosquito's labium is 30 micrometer. So in this one, our main objective is to create some kind of sensors. In the kind of sensors, we don't need to extract much amount of blood from your body. A very little amount is okay. That's why this 30 micrometer would help to extract blood from your body in a painless way for any sensing measurement. So, as I said, the 30 micrometer, the mosquito's labium is giving very less pain. Why? So you can see here, this is a cross section of the skin structure, and here is the micro needle, and here is the commercial needle. You can see how much depth it can go inside the skin. So if it goes this much depth inside your skin, what it will do is, it will disturb the pain nerves, because once your pain nerves are getting disturbed, you will feel the pain. But in the case of micro needle, it is only on the surface, so that it will not disturb the pain nerves, so you will not feel any pain. Anyway, if you give some drugs, it will automatically go and mix up in your bloodstream. So there are some different kinds of microneedle available, like a solid microneedle, coated microneedle, dissolving and hollow microneedle. So in this topic, I am going to speak about only the solid microneedle and the hollow microneedle. So as I said before, the mosquito's labium length is around 3 to 4 millimeter, and the diameter is around 25 to 30 micrometer. You can see here, this is artificially created in our laboratory. It is a titanium microneedle. So which is having the same diameter, like a 25 micrometer inner diameter, and the outer diameter is a 50 micrometer. You can see the length, it is very clear. We use the sputtering technology to create this one. So here I will show how we did this. Because inside the sputtering, we have this kind of setup. What it will do is, we fix the copper wire here, and then we do the sputtering. And when the target molecules go on here, it will just in the whole layer, it will start depositing. Instead of depositing thin film on a flat layer, we use the needle, and then we coat it on the surface of the needle. And then finally, what we do is, we etch out the core needle using the HF solution, so that you can get the hollow structure. So I have said we just created the titanium microneedle, hollow microneedle, and we need to evaluate whether it is working similarly as the mosquitoes bite or not. So for that, we fix the microneedle here with piezoelectric actuator. The piezoelectric actuator is, it can give the negative pressure as well as the positive pressure, so that it can extract the blood from your body. So here we use some simple test setup using titanium microneedle as well as other two microneedle like an Nanopath 33 and stainless, which is procured from the company. And we use three kinds of microneedle, and the extracting solution is blood and water. So as I said, the female mosquito can extract 1.9 microliter for 2 minutes. So here we use the flow rate evaluation. You can see here sample 1 to 3 is a Nanopath stainless and titanium, and this is 456 for the water. 1 to 3 is for the blood, and 456 is for the water. So you know very well, the blood is more denser, so we cannot extract very easily. That's why the extract rate of blood is very little, 7 microliter per minute. As I said, in the mosquito's labium, it can extract 2 microliter, approximately 2 microliter per minute. In this titanium microneedle, have the inner softer surface, so that it can extract more blood compared to the mosquito's labium. In the case of water, it can extract more than 40 microliter. So which is also another advantage. We can use it for some other purposes also. As a next evaluation, the first evaluation is the flow rate evaluation, and the second evaluation is the pain evaluation. Because there is no unit or no analytical net for measuring the pain directly. That's why we use the indirect method of alpha amylase activity. What we do is, we take the lab grown mice, and in the leg we puncture it using our titanium microneedle, and then immediately we extract the saliva. Because when person is feel more stressed, the saliva in the salivary alpha amylase activity will be much higher. So indirectly you can measure if the salivary alpha amylase activity is very low, it is not feeling any pain or stress. If the salivary alpha amylase activity is very high, it means that it is getting some pain. So accordingly we can use. So instead of using that only the 25 micrometer titanium microneedle, what we did is, we just take some different microneedle. The control is 25 and 35, 70, 95, 100, 150, 200, and then we evaluated the same test. So finally, what we found is, if it is a less than 95 micrometer, the alpha amylase activity is very low. So which means not getting very stressed, or not getting very pain. But once it exceeds the 95 micrometer diameter, that means the mosquito's labium, so the pain is getting higher. So we limited our research into less than 95 micrometer. So after that, then the final evaluation is, we have to test the flow of that one. So here we attached a small glass tube, and here is the microneedle. We pass the water here, and then water is coming out on the other side, and there is no leak here. And with the help of company, we developed this wristwatch type sensor device. So it has the 4 microneedle. You can see here the microneedle is fixed here in the four part, and we just wear it as a wristwatch type. So what it will do is, it can, using the piezoelectric actuator, it can puncture your skin and extract the blood, and it can sense its glucose level on the wristwatch itself, and then it can give you the results. It is more convenient for the people who are affected by the severe diabetes, because they have to do the test for every day at least 5 or 10 times. In that case, this device can be really helpful for them. So automatically it can measure, it can puncture, and it can measure, and it give you the results about your insulin level and how much insulin you have to take for your body. So this will be more helpful, and we already developed this device, and we are trying to make it small now. So how the microneedle, because previously until this one, what I have spoken is the hollow microneedle. microneedle. So you have to extract from your body the blood or something in a painless way. On the next step, instead of extracting, you can measure something in your body itself. That's what the solid microneedle pH sensor came. Why I'm saying is here pH sensor is, in this case, in the whole research, what I have taken the biomarker is pH. For the pH, so using the pH, we can identify different kinds of diseases. So, as I said before, for developing any point of care devices, we have to consider two things. One is the biomarker, and another is the material. So, this whole research is based on developing pH sensor for particular diseases. So, average human cell ranging from 5 to 100 micrometer, you know very well, because each part of our body cells have the different sizes, which is ranging from 5 to 100. But each and every cell, if you take in some body cell, and if you are measuring the fluid inside the cell, and the fluid pH range will be 7.1 to 7.2. That is a normal range for a healthy person. But if in some part of your body having some other cancer cell or something, if you measure the pH of the cancer cell, it will be around 6.2 to 6.9. So based on this difference, we can identify the cell, because instead of going for a high cost technique, using this simple pH sensor technique, you can identify the cells, whether it is a normal cell or cancer cell. Same kind, you can measure the temperature also inside the cell and measure, because the cancer cells are more warmer than the normal cells. Using this temperature gradient different also, you can identify whether the cell is healthy or the affected already. So these are some of the technologies in the recent advances in the single cell technology. So I want to confirm one thing, why I am saying single cell pH sensor every time. So you can say, I can say simply the pH sensor. The importance is there is no single cell pH sensor is available till now. Because the problem is now we are in this pandemic, we are facing a lot of trouble in creating some new vaccines for the COVID also. The main reason for that one is, if you want to develop some drug in an easy way, what the commercial pharmaceutical industry do is, they take the petri dish and grow the particular cells, and then they can give the drug, and then they can take the average data from the millions of cells. So in this case, there is no technology available to analyze how the single cell is acting for that particular drug. If they develop some technology like the single cell pH sensor or any sensor for the single cell, it is more helpful in developing drugs in a very easy way, in a fast way. So that we are using single cell pH sensor for identifying some diseases. See, these are the other researchers have used for the single cell pH sensing technology, like a nanopipette sensing technology and fiber optic probe and single cell photoacoustic thermometry also. The problem with this technology is they are using some quantum dots, which is highly costly, and pH sensitive dyes, and high cost for fabrication, and instrumentation difficulty, and cytotoxicity also. So we want to get rid of all the technical difficulties. We want to measure it directly in a fast way. That's why we use a new technique. So here you can see this is a tungsten rod of 300 micrometer, and we coated with the AgCl and the zinc oxide by the sputtering method. So the AgCl is the reference electrode, and zinc oxide is the working electrode. So what we do is, when we put these two electrodes into something, a solution or some fish egg something, so it can we can easily identify the potential difference between these two electrodes. So we always, what we do is, first step, we in the laboratory, we purchase the commercial pH solution and test the pH. And the second step, we just use this kind of a fish egg. And third step, we use the animal studies. So in the first step, we just use the pH solution like this here. And the second step, what we do is, we here using the we take the fish egg and with the addition of citric acid. That means we are artificially changing the pH of the particular medium, say inside the fish egg. So here is the fish egg. You can see here is the needle is punctured, and the two electrodes are connected here, and we are checking the potential difference, like open circuit potential here. So here it is giving us a linear relationship. So that means according to the pH change, the sensor is working well. On the second step, what we did is, we take the mice, and the mice brain was operated, and in the mice brain we injected some two micro electrodes. So the one is the AgCl and another one is the zinc oxide. So here you can see this is from the commercial pH solution readings. So in the commercial pH solution reading, the reading was stable for a long time, so that we assume that the sensor is working well. And in the mice brain, we tested here. So you can see here the pH 7.13. It is the mice cerebrospinal fluid. We usually simply called as CSF. So the theoretical value, that means we take the liquid from the mice brain and evaluated using the commercial pH meter to confirm our microneedle effectiveness. So here this is the estimated value by the microneedle, which is having the 7.03. So you can see the difference here. Almost 85% the data is matching, but still the 50% error is there. Why? Because when we created this AGCL or zinc oxide electrode, the surface is little bit rough. So when we try to puncture the mice brain or mice bladder, what it will do is the brain tissues and blood is affected this open circuit potential. That's what now we are trying to make it more smoother surface and using some anti-fouling materials also. So here I said there is a two needles, two micro electrodes simply called. So we want to make this process more easily. That's what we thought. Why don't we put these two electrodes on a single micro electrode? That's what we came up with this method. So in this method, you can see the same tungsten wire, and using the electrochemical etching, we see here. We changed it to 4.8 micrometer using the electrochemical etching, and using tungsten is a metal. When we do the open circuit potential measurement, the metal will affect, so it can create some interference. That's what first initially we coated with the SiO2 layer, and then SB2O3 and AgO3. This is our lab developed material for the pH sensor. So you can see here, these two materials are coated on a single microneedle using masking, and finally the structure will be like this. The red color is the working electrode, tungsten SB2O3, and this color is means for a AgO3 reference electrode. These two electrodes, and here is the contact. So when you use this one to puncture something, these two electrodes can come into contact with the medium, and then it can give the potential difference. So initially you can see this is the final microneedle structure, which is compared with the 1 yen Japanese coin. And here you can see the tungsten, initially it is 300 micrometer, and finally it became 343 micrometer after all the layers of deposition. So we use the electropolishing condition like this, copper and KOH aqueous solution, DC voltage, and time is for 90 seconds. So this is the SEM picture of the microneedle here. You can see, as I said, two electrodes on the same needle. One is the working electrode and another one is the reference electrode. See, this space is the SB2O3. This is the working electrode, and this is the interface here, and this is the AgO3 reference electrode. So we mounted these two electrodes onto the single microneedle for measurement. You can see, initially we tested with the XRD to confirm the material SB2O3 and as well as the AgO3. And here you can see the cross-sectional one. The core is the tungsten, and the first layer is the SB2O3, and then you can see the clear layers. The layers are separated because of the different materials, separated by the SiO2 layer. And even the SiO2 was confirmed with the EDS spectra, energy specific X-ray analysis. So you can see the SB2O3 was in the green color and AgO3 was in the blue color. It was separated, and we want to check the interface here. You can see this is a cross-sectional image of the one, and SB2O3 and AgO3 is in the red color, and it was separated by the SiO2 clearly. And here there is some damage because we just cut the needle by the hand for the cross-sectional. That's why we cannot able to get the clear picture of that. So after creating the needle, as I said, I want to test the needle with a single cell. So we take the HepG2 human liver cancer cell, and this is a microscope, and this is a microneedle, and here is the single cell. And you can see this is a single human liver cancer cell. We tried to puncture using this one. We have just tried so many times because when we try to puncture, some cells may be damaged and we cannot able to puncture the cells, and the cells are keep on moving to some other direction. So that's what we are facing so many problems when we try to do this. And finally we achieved and punctured the cell, because each cell have some intercellular fluid. So we want to measure the pH of the intercellular fluid only. That's why when you puncture the cells, the needle, you have to be very careful. The intercellular fluid should not come out. That's why we just carefully punctured, and in this case we successfully punctured the needle into the single human liver cancer cell, and we successfully measured the pH inside that one. So now what we are doing is we are artificially giving some other nutrients to change the pH inside the cell, and then we do that. So the challenge is what we have faced is it is highly difficult to probe and puncture the cells because the cells are sometimes it is floating and sometimes it is attached to the base of the substrate, and the small vibration by hand can lead to failure because for making each needle, for making this kind of a one single micro needle, it will take at least 8 to 10 hours of time. And then using this kind of cell culture, everything, using a simple hand vibration can damage the experiment completely. That's what we wanted to develop some automated system for that. So with the help of a Mehra Corporation Yamaguchi, we developed this instrument. So this is, as I said, the Nikon. We are having so many microscope. With one of the Nikon Eclipse series microscope, we attached this kind of instrument. So what it will do is it has the XY movement, and it is programmed to move and move forth and back. So what it will do is we can identify the cell and then we can program it. You can go puncture for 30 seconds and then measure and stay for 30 seconds and come back. So it can do everything. Also, it has the additional advantage of giving vibration. As I said before in the first slide itself, when the mosquito bites your skin, it cannot go directly. It can give some vibration and then it can puncture. So we want to artificially create vibration also in this device. So here we put some frequency generator, so it can create some frequency and then 4500 hertz frequency, I think, and then it will puncture using that vibration. So you can see here before puncturing. So as I said, as we can program it actually. So using this micro needle, we programmed it. So before puncturing itself, it started the measuring. So before puncturing, it was 85 millivolt, and after puncturing, it was 135 millivolt. So with this difference, you can identify how much pH, what is the pH of in the fluid inside the cell. Based on this one, we can identify whether the cell is a normal cell or the cancer cell, something. So the next step is, as I said, we are facing some difficulties in probing the cell because it is in the base. So when we try to puncture, it is keep on moving. So we have to put some cover or something on the cell so that it can be stable until you puncture and do the measurement. Because it's automated one, we cannot identify easily. So we go for the nanosheet technology here. So the nanosheet is a simple polymeric nanosheet using made up of polylactic acid. So we do the spin coating method. So initially we use the PVA, polyvinyl alcohol, which is a water soluble polymer. And again, the second layer is coated with polylactic acid. And finally, we put the substrate into the water so that PVA, polyvinyl alcohol, can dissolve in the water, and only the polylactic nanosheet can be floated onto the water so that you can take it out and cover with shell. So it can completely cover the shell so that when you puncture, it will not move. The cell is fixed on the same place. So even we use the porous nanosheet also, because you may ask, when you cover the shell with the complete polymer, whether the cell can die easily. But in the case of porous nanosheet, using the pores, the nutrients can go inside and the cell can be lived for more days. You can see here. So this is a fish shape and coated, covered with the nanosheet. It is completely captured in the nanosheet and fixed on this in some place on the slide. So when we try to puncture, this fish shape cannot move. Even in the case of cell also, it cannot move, and it will be in the same place. So it will be more helpful for the measurement. You can see here. So this is we developed some two different kinds of nanosheet, like a 200 nanometer and 60 nanometer, and a thicker nanosheet as well as the thinner nanosheet. So with the 200 nanometer, the thickness is very high. So when we try to puncture, what it happened is the nanosheet is attached with the needle. It is coming out. It is a problem due to the air struck inside here. And in the case of 60 nanometer, it is completely covered the nanosheet, and then it is very easy for us to puncture and do the measurement. And you can see here in the fish egg, inside the fish egg, there is a vibration. As I said, we are giving some vibration for the puncturing. The vibration at the needle is confirmed here. In the fish egg, inside the fish egg, you can see it has started vibrating inside the cells. So not only a single micro needle, we are using some kind of micro needle arrays also. So there is a major difference between the single micro needle and the micro needle array is if you want to deliver something, because there is a two thing. If you want to deliver some drugs or something to your body, you have to use the micro needle array. If you want to measure something in your body, you can use the single microneedle, because when you want to deliver some drugs to your body, it needs large amount, say for 1 milliliter or 2 milliliter. Using the single microneedle, it is impossible to deliver that much, because it needs to be punctured continuously. But in the case of microneedle array, it is very easy. Within a one single patch, you can deliver more drugs to your body in a painless way. So moving to the next topic, like electronic skin, as I said before, the nanosheet. So why the nanosheet is important here? So current healthcare system faces daunting challenges in developing some other on-body sensors. So usually this is called as an on-body sensor. The sensor will be like this. Into your skin, it is attached like as a tattoo, and then it can measure something from your body temperature or body pH, as well as the sweat also. So why the electronic skin technology is more advantageous is, so when you are using the blood, it is cause pain, as well as invasive, and saliva, it is a minimally or non-invasive, no pain but low analyte concentration, because in saliva, low analyte concentration, and as well as the tears, it is also minimally invasive, can cause little pain. But in the case of sweat type sensor, it is minimally or non-invasive, no pain at all. That's why these electronic skin sensors can be used as a for electronic skin sensors. So this sensor is a printed electronics, is a good candidate for low cost flexible sensing application. So when you measure, when you make something electronic skin like a polymer nanosheet, and then you can print electronics on top of that, and then it can do its job. So see here, this is a PDMS based nanosheet, and then the sensor is deposited on the top of the nanosheet. So titanium and AU are the electrode, and the PDMS is the base layer, and acetyl cellulose as a sacrificing layer, and AgO3 is based O3, which is having the same material what I have used in the microneedle sensors also. Here the platform is just different for the skin sweat sensor, like a skin dehydration sensor. So here you can see we have done the experiment with the pH solutions like 4, 5, 6, 7, and then it is having the good linearity. And we tested with the 3 times, it is also having the good result. And then we tested with the 3 hours also. So once you attach the sensor on your hand, and then we artificially provide the sweat, and then we measure, and it is having the good result. So even as I said, it is like a kind of tattoo. Some people may have asked, may have a question, if it is having a tattoo-like structure, if I'm staying indoor and I'm just walking outdoor, so the temperature gradient can cause some disturbance. That's what we did this experiment. So the nanosheet here, you can see it is on my hand, and then we artificially using the hair dryer, change the temperature artificially. So this is the room temperature here, 32, and then we change it to 34.9 and 38.2. So using this temperature difference, so here you can see, and the artificial sweat also we tested, and there is no difference here. Almost the polymer, the nanosheet is not affected by the temperature. So recently it was published in ACS sensors, and it was selected as a cover image also. The thing is like this, it is a skin and you are getting sweat and pH electrodes on the inner side of the nanosheet. When you are using this one onto your skin, automatically it can measure the pH from your sweat, and then it can send data to your smartphone also. And this is a pamphlet developed by your university, Your Health in Your Hands in the topic, and novel wearable technology easily detect heat stroke. So the why that using heat stroke is, in Japan in summertime, many people are affected by the heat stroke, because using this kind of sensor, making it low cost and wearable and adhesive free. No adhesive is required because it is very thin and very soft and highly flexible and durable and flexible also. Even though if you bend or twist or something, the sensor cannot be damaged. So using this one, the same sensing material we used in the mouthpiece device also. So in the mouthpiece device, we put the same material, and this is our lab student. We asked him to drink mineral water, black coffee, and Coke. So each are having some different kind of pH level, like a pH 7.0, pH 5.6, and 2.4. And we here in the picture I'm showing only one sensor, but actually we put 3 sensors in 3 different places, like a near front teeth, near canis, and near the back teeth, so that when the person drinks, we can identify which part of your mouth is giving more accurate result and more highly reliable result. That's what we just analyzed pH 7, 5.6, and 2.4, and here it is giving the back, near the back teeth, having a more sensitive region. So it can. So we finally fixed the region near the back teeth, and then we started doing some other experiments also. We are trying to increase the sensitivity of that one because, as I said before, in our university we have a lot of Olympic medals we have already received, and so many athletes are training each and every day because they are continuously practicing, so they are affected by the lack of hydration. So when this mouth pH sensor works well, so that it will be more helpful for the athletes. So it can because easily we can recognize the dehydration for the athletic people. Moving to the next topic, microfluidic devices. Many people know microfluidic devices can use very low volume. As I said, in the microneedle sensor, the hollow microneedle, when extracting the blood, it is some 5 to 7 microliter of blood it can extract. So when we use that kind of a very little amount, you cannot use the commercial technology for the analysis. You have to use the microfluidic devices because it requires only the very low volume, like in a microliter or nanoliter, and very little disease reagent consumption, and shorten the analysis time and reduces the overall cost of the analysis. So that we are using the microfluidic devices to identify the circulating tumor cells. So people know metastasis are the cause of the 90% of the human cancer cell. Metastasis is nothing but there is some primary tumor, and as the days go on, what it will do is the primary tumor cells mixed up into the bloodstream, and then it can form the secondary tumor, which causes the patient's condition very worse. So if you find the circulating tumor cells in the initial stage itself, it is very easy to cure. That's why we are developing some kind of microfluidic devices for the detecting circulating tumor cells. So the CTC, the circulating tumor cells, can help early detection of cancer, and the choice of cancer therapy can be chosen. And number of CTCs in blood is in relationship with prognosis of cancer, and monitor cancer treatment response also. So what this microfluidic device can able to deal with a very small volume extracted from the microneedle, and no pre-labeling or pre-processing of the blood. So this is a microfluidic devices developed in our laboratory, which is having the material of AgCl reference electrode and zinc oxide working electrode. And the microfluidic channel was created using the commercial photolithographic process in the clean room. And the microfluidic channel width is 140 micrometer. As I said before, the human cells ranging from 5 to 100 micrometer. So we limited our microfluidic channel up to 140 micrometer. See, this is our experimental setup. So this is a syringe pump, and here is the pH buffer solution purchased from the company, and here is the inlet for the microfluidic device, and it is passing through, and then outlet it is for the trash. So when we pass the pH buffer solution here, it started because initially this area is filled with air. So we mentioned as a dry condition, and then the liquid is started passing through this microfluidic channel, and after some 27 seconds, it becomes stable. That means the liquid is passing through both the electrodes, and it can give the open circuit potential, say for the potential difference here. So in everything we have the dry condition, and it is passing through, and there is a stable response. So it takes around 30 seconds to get it very stable. That's what we can say the response time of our sensor is 30 seconds. On the next step, what we done is we take the real cells like a human lung cancer cell, rat muscle cell, and dog kidney cell. So here we instead of a pH buffer solution, we take the cell solution, and here the DMEM is a medium we have used here, and these are the microscopic images of the cells. So we do the same because using the same measurement. Yeah. Could you please mute? Okay. We are using the same measurement conditions here. So DMEM, this is a medium. So black color is the medium. So here only the medium, cell medium is only passing through. And then DMEM plus A7R5. A7R5 is a rat muscle cell. So both are having the same pH. There is no pH change between the cell. But in the case of MDCK, dog kidney cell, and the lung cancer cell, when we pass through the microfluidic device, it is having the potential difference. You can see DMEM only cells having some different 0.6 volt and 0.26 volt, and here it is a 0.22. There is a 400 millivolt difference is there. So with this one, we can identify when you pass through some cells along with the circulating tumor cells inside. So it can give some fluctuations based on this one, so that we can identify in the blood contains some circulating tumor cells. So this is the initial research we have to there is a long way to go to develop completely the CTC detection microfluidic sensor. So even not only the photolithographic method, we can use some DOA ideas to create microfluidic devices too, like a xerography based microfluidic device fabrication using the cutting plotter. The cutting plotter is nothing but because it is easily available in every cities. They are creating some stickers for the number plate, right, for the car and bike. That is a cutting plotter. You can design something and give it to them. They can cut and give you the pattern, and then you can laminate between two sheets, and then it can act as a microfluidic device. It is a very simple way of creating a microfluidic device. Not only the xerography based method, even we can use some paper based disposable microfluidic also. With a simple filter paper and the wax crayon, you can create this kind of microfluidic device, or some colorimetric sensor like a pH paper and blue paper like this. So it is very easy. So you can draw the design and heat up. The wax can melt down, and then it can create a hydrophobic coating on the other area with the hydrophilic, so that you can create the pattern easily. So finally, coming to the conclusion, so the main major research of this topic is to create a single microneedle sensor and the microfluidic sensor and mouthpiece sensor, as well as the electronic skin sensor. So this is our major breakthrough in developing the single microneedle sensor. Using the single microneedle with the commercial multimeter, the pharmaceutical industry can easily use this one for the early drug discovery, and it can be easily integrated with other point of care devices too, like a microfluidic device, and can it modify it for the multiple analyze. As of now, we are focusing only for the pH and temperature, and we started for the glucose also. There are so many biomarkers available, we can easily tune easily. And the next step, we are going further measuring neuron membrane potential, because in the Alzheimer and Parkinson disease, it is very hard to measure the neuronal imbalance. So say for a ionic imbalance, we can say. So we try to puncture the microneedle into the neuron's axon, and we want to continuously measure by giving some drugs and how the imbalance can be cured. And these are the current challenge we are facing now. There is a adult skin as well as the child skin, which is having some different composition. As the doctor suggested, they asked us to do some different experiment for the child skin also separately, so that it will be more helpful for the child, because the child they are very afraid to go to the hospital due to this injection. So they asked us to create more faster way to create some drug delivery, as well as the extracting some blood for the child in a painless way. Yeah, thank you very much. Thanks for your time. Maybe you can ask any questions if you want. Are there any questions from the audience? You can unmute and ask me.
So this is Amrish. Do you hear me, sir?
Yes, sir.
Hello?
Yes, sir, I can hear you.
Yeah, it's a nice talk, sir. Impressive. I think it. I like your presentation and I like your work. It's really, great to hear your research work.
Thank you.
Actually, for me, I think I'm hearing for the first time about the paper-based microfluidics. Actually, I'm a physicist, but I'm also working closely with biology.
Okay.
I'm looking for something like microfluidics based on paper-like, but I'm looking for a transparent material. Is it possible, sir?
You mean transparent material? Because you want to use the filter paper-like structure, and it also should be transparent.
Exactly.
Okay.
Yes, sir.
The best way is we can do the electrospinning of some polymers. We can do electrospinning of some polymers, and then we can make use this kind of same technology. Because I don't have any idea about the transparent kind of material, which is similarly like a filter paper. Maybe I will let you know if we some materials.
Sure, sir. Also, since you are good in your research area, did you ever heard about having this transparent based microfluidics? Like, if so, maybe this will be nice, or we can make some. We can propose this to start working on this.
You want to use the xerography based method or the filter paper method? Which one you are preferring more?
The not the filter one, the other one, sir.
Other one can be used, can be made very easily. That is not at all, because using, when you contact the sticker shop, you can design something in the AutoCAD. You can create some microfluidic device, and then you can contact the sticker shop. They can cut it and give it to you. You can use that one as a template. Maybe I can share some photos with you later, because I have some photos.
Sure, sir. We will have a separate discussion, but it's a very nice work, sir. Impressive.
Yeah. Thank you.
Thank you.
Thank you so much, sir. So, dear participants, if you have queries or questions related to the biomedical and bio nanomaterials, you can ask now. Thank you. Sir is ready to answer for your questions. So, you can unmute yourself and you can ask questions. So, I think.
Yes, I'm okay with Tamil also. Maybe just don't worry. Don't hesitate to ask anything.
Yeah, okay, sir. So,
Yeah.
பார்ட்டிசிபென்ட்ஸ் வந்து தமிழ்லையும் கூட கொஸ்டின் கேட்கலாம் சார் கிட்ட. ஸோ அதனால நீங்க வந்து கொஸ்டின்ஸ் கேட்கலாம். He is ready to answer in Tamil even.
Someone asked, can you suggest one application of MOO3 now in the nanoscience field? The best application for MOO3 now, they are using it for only for the gas sensor, as far as I know. I don't have any idea about some other applications at this moment.
So do we have any other questions? You can ask. Sir, I'm having one question.
Yes, ma'am.
So you have told that we can inject micro needles in which we can inject the insulin or so. So will it cause any kind of side effects to the patients? Why? Because it will be in their body for longer time. So will it cause any other side effects like so?
We are actually studying for each and every microneedle. The first thing what we have to do is a cytotoxicity test. So even for 2 or 3 days, we just put the needle into some cells, as I said, the cancer cells or the blood, and then we put the needle itself alone for 2 or 3 days, and each and every day we evaluate whether the materials can cause some cytotoxicity or not, and then only we just go for the next step. Because even in the first step itself, if it is started some toxic effect, we just stop the research and change some other material. As of now, using this material, it did not create any side effects, even for 3 days. We just measured the maximum of 3 days only.
Okay, sir. Okay, sir. And one more question. So you have told about the mouth sensors. So
yes.
What are all the types of materials that can sense? Why? Because if I'm taking a drug, it will be having some component, and if I'm taking food, it will be having some component. So likewise, so how far or how much types of components that can be sensed by that mouth sensors?
I think your answer is infinity. You can just change the material for the particular biomarker and then you can use it. In our case, we just want to detect only the pH, so we used the pH sensing materials in the mouthpiece. And if you want to detect something from other biomolecules from your saliva, you can accordingly change the material and you can use the same device also, mouthpiece device. Even you can put some multiple sensors on the same mouthpiece device and you can analyze.
Okay, sir. So, dear participants, do we have another doubt? Sir,
Can I ask a question?
1 minute, ma'am.
Yes, ma'am.
Sir,
Yeah, sure.
please wait, sir. Ma'am, again.
Hello, Dr. Ganesh Kumar. It was a very nice lecture. Actually, I have a very kind of general question, though it's related to cancer. I just wanted to know how much the fourth stage cancer in the brain is treatable now. Like how much on the market. I'm not talking about the research level. Obviously, you must have research is going on at a very good level, and people are trying, but at the market or for the patient, how much has that or how many years do you expect that the fourth stage brain cancer is treatable, or or you could increase the life expectancy of the patient? So I know it's a very general question and asking you, but I just wanted to have a general
Yes,
scenario.
ma'am. It's look always like a prevention is better than cure. So if you want to detect the cancer in the early stage itself, it is far better than go for some severe treatments. But till now, maybe in 2025, the Neuralink company is going to release a chip, so which can be implanted in your brain, so that it can monitor all the activity. So if there is some irregularities, it can inform you in the earliest stage itself, and then you can go for the treatment. That is the easiest way as of now. That is a more farther development at this moment. So
So
it's
you
going to
mean
be
that
released in 2025 by Neuralink.
okay, so you mean that mostly like maybe above certain age, everybody should have the chip in the head if they are. Is that
Yes.
okay?
Yes.
But that would not be a very feasible thing for everybody, and I'm sure it's going to be expensive. And yes, or how do you think that chip in the head would affect the general health? But yeah, it's a good thing you're told. That's something new I've heard. But so actually, there is. And the thing is that for brain cancer, sometimes till the fourth stage, you don't realize that you have that.
Yes.
So just like that, even I think maybe in abroad, there is thing like after every 10, after about 50 years, people have a general checkup, but that's not the case here in India. So yeah, right. So, but anyway, thank you so much.
It is suggested to go for a health checkup at least once.
Health checkup, yeah, sure.
Yeah.
30
is
years
the
old.
easiest way for the prevention.
Yeah. Okay. Thank you so much. This is very general, and but anyway, thank you for your information.
Thank you. Thank you.
Thank you so much.
Thank you.
So, dear participants, do we have any questions? Sir, I think there is no more questions, and there was a good presentation, and it is more informative. Yes, sir. Yes, ma'am. Sophia, ma'am.
Yes. Sir, it was a very informative talk. I'm Dr. Sophia. I have a material science background. So this biosensors is quite new to me. So just for gaining knowledge, I've been listening. It was very interesting. So if anyone wants to start any like experiment to measure, like develop a pH sensor to start with, like for example, students, BTech students or MTech students, they want to start anything, what would you suggest? Like, where do we start with?
You want to develop some pH sensor. I'm not sure about the knowledge of our bachelor students and which way they want to proceed. So we have to look for the facilities also. What are the things available in the institute? So based on that one, because as previously I just spoke with the dean, right? He asked about the microfluidic sensor, which is very easy to construct even at any city. But in the case of microneedle, it is quite hard to do the fabrication as well as the measurements. That's why I can suggest that maybe based on the research facilities available there, based on that one, we can formulate some research ideas and we can give it to the students, then we can get the result.
I see. Okay, sir. We have a pharmacy unit with us. So even though it's an engineering college, we have some collaboration with the pharmacy department. So you're saying that microfluidic devices probably are easily fabricated, right? More than your pH sensor.
Yes.
So if you can, guide us little bit about like where we can start with, or like if you can help us, it will be very great. We can actually start an experiment.
Okay, we can have some separate discussion later. Then I can give you suggestions. Then accordingly, we can have a research.
I'll drop an email. Yeah, thank you very much, sir.
Okay, ma'am. Thank you.
Thank you, ma'am. And thank you, sir. That was a very informative and impressive talk. Why? Because it is a new field for us, and many researchers are going on. And thank you for your kind acceptance of our invitation and
thank you.
Presentation. And I now call upon Dr. N. Bhuvaneshwari ma'am to deliver the vote of thanks for this session. Ma'am.
Thank you, ma'am. Thank you.
Thank you, ma'am. So, thank you, sir. So, dear participants, we are having one announcement for you. So, we'll be shortly starting our presentation session. So, those who are having a slot, so you can be ready with your presentation and be in your Google link. So, the same link will be used for the thing. And we'll be having a feedback link and active participant quiz. So, complete that in a time. 1 minute. So I'll be sharing the link. Sir, thank you so much, sir. So, dear participants, the active participant quiz link and feedback link is in the chat box. You can use that.